Welcome to this introductory video on the topic of vectors. We're going to look at a couple of vectors here. A vector is a quantity that has both a size, called the magnitude of the vector, has a length or a side, but it also has a specific direction. So if we draw a line to indicate the horizontal, and measured this angle from the horizontal to the vector, that's how we represent its direction. So this vector has a length and a direction, an angle of say 35 degrees. This vector, however, has quite a different direction, a much larger angle. So although the magnitude of the vector it may be similar to the magnitude of the first vector, its direction is considerably different. It might be at an angle of, say, 60 degrees from the horizontal. So we're going to look at what happens if we try to add two vectors. That's the main calculation that we need to be able to perform in this unit. So suppose we have this situation where perhaps we're on a trip somewhere, and maybe we're a little bit lost. So we travel a certain distance in a particular direction. Then check our map, get our bearings, change directions, and keep going. If we try and add these two parts of the journey, we could represent the experience, or the total journey, with a different vector that has a total length and its own particular direction. All right, and that vector, that second vector that is shown here in purple, or I guess it's a third vector, sorry, this vector shown in purple is what we refer to as the resultant vector. And it has the characteristic of representing the journey if it were taken in one direct line. So it takes the pieces of the journey, or the individual vectors, and gives us a vector that represents the overall or total journey. And this is the resultant vector that we are going to learn to calculate. The method we're going to use to add two vectors and determine the resultant vector is some basic trigonometry. We're going to break each vector into its horizontal and vertical components. This vector has a horizontal and a vertical component. This vector also has a horizontal and a vertical component. If we calculate the horizontal components of both vectors and add them together, we end up with the horizontal component of the resultant vector. Similarly, if we add together the vertical components of the two vectors, we end up with the resultant vector's vertical component. So we'll go through now the basic steps for calculating the horizontal and vertical components using trigonometry. So let's begin by calculating the vertical component of the vector. Suppose our vector has a magnitude of 100 and a direction of 60 degrees from the horizontal. If you recall, the sine of an angle is equal to the opposite side divided by the hypotenuse, or the ratio of the opposite to the hypotenuse. So, in this case, the sine of 60 would be equal to y, the vertical component that we're looking for, divided by 100. Rewriting the equation, we can say that y, the vertical component we're looking for, is equal to 100, the magnitude of the vector, times the sine of 60, the direction of that vector. We can calculate the horizontal component of the vector in a similar way, recalling that the cosine is defined as the adjacent divided by the hypotenuse, or in this case, the horizontal component over the magnitude of the vector. Rearranging the equation, we get x, the horizontal component of the vector, is equal to 100, the magnitude of the vector, times the cosine of 60, the vector's direction. So returning now to the example where we are adding two vectors to obtain a resultant vector. We'll look at this case of an 80 amp vector with a direction of 35 degrees from the horizontal, and a 100 amp vector at a direction 60 degrees from the horizontal. Using the trigonometry that we've just reviewed, we can calculate the horizontal component of the 80 amp vector to be 80 cos 35, and the vertical component to be 80 sine 35. For the 100 amp vector, the horizontal component will be 100 cos 60, and the vertical component will be 100 sine 60. Now, to calculate the horizontal component of the resultant vector, we add the two horizontal components of the original vectors. So the horizontal component of the resultant vector will be 80 cos 35 plus 100 cos 60. Similarly, for the vertical component of the resultant vector, we add the individual vertical components. To obtain a vertical component of the resultant vector that is 80 sine 35 plus 100 sine 60. So performing those calculations for the horizontal component, 80 cos 35 plus 100 cos 60 gives a horizontal component of the resultant vector, which is 115.5. Similarly, for the vertical component, 80 sine 35 plus 100 sine 60 gives a resultant vertical component of 132.5. So now that we've calculated the horizontal and vertical components of the resultant vector, we can use the Pythagorean theorem to calculate the magnitude of the resultant vector. Recall that if we square the both short sides or legs of the triangle, add them together, we obtain the hypotenuse squared. And so the hypotenuse length is the square root of that sum. So we will square the horizontal and vertical components, add them together, take the square root, and obtain the magnitude of the resultant vector, 175.8 amps. So we know that the magnitude of our resultant vector is 175.8 amps. But recall from the beginning of the video that a vector has both a magnitude and a direction. We know the magnitude or the length of this vector, but we haven't yet determined its direction. So we return to trigonometry, recalling that the tan of an angle, we can call this angle we're looking for x. So the tan of an angle is equal to the opposite over the adjacent. So we know the opposite and the adjacent lengths. We can obtain that ratio, use the inverse tan function, and calculate, finally, the direction of the resultant vector, which will be 49.9 degrees from the horizontal. We write the final answer for the resultant vector as 175.8 amps at 49.9 degrees.